Go over a couple basic things in the very beginning here. So, I'm Joel, Head of Operations for Tracer. Presentation today will be focusing on LiDAR, specifically how this technology is going to be used within land acquisition and land development, and really focusing on the basis of what LiDAR is and the basic principles and theory behind it, and then how it can be leveraged within these workflows. So feel free to ask any questions you have in the Q&A dialog box, and we'll get to them at the end. I just want to run through the presentation as a lecture, and then from there we'll shift gears and we'll focus on those questions, provide answers. And if we don't have the full amount of time to provide answers to every question, we'll follow up with emails thereafter with individuals to ensure that those questions are answered. And there'll be an email at the end of the presentation that you can direct those questions to if you don't get an email directly back from us, which you will. You can always reference that email address to connect with us directly. All right, well, let's get started. So yeah, today's focus, LiDAR, and how this is really going to incorporate these data sets that we derive from LiDAR, how they're really incorporated into the land acquisition and the design stage components of construction. So let's jump in. So LiDAR, a really quick intro to LiDAR and what it is. So LiDAR is light detection and ranging. That's an acronym. And what it's really referring to is this emitting source having a sensor that can emit a laser and bounce it off of a surface and have it received by a receiving device. And in that time it takes for the light to be emitted from the emitter and received by the receiver, that time is what allows us to calculate the distance between these objects, the sensor and receiver, and the surface we're trying to measure in itself. Works just like your handheld LiDAR measuring device at home that you'd use in your home construction projects or on a job site. Very straightforward, literally just using time differencing to calculate distances from the emitter sensor and the object itself. Very straightforward. It's been around for a while. Quite a while. It's been on aerial platforms and handheld and mobile devices for a while. So yeah, it's a proven technology, and it's only become more available and more accurate as time goes on. We're seeing a very positive trend in terms of being able to have easier data acquisition with LiDAR relative to historic times, and it becoming less expensive in general. So this is a great tool for us to start leaning into more often and helping us reduce our risk in the land acquisition stage, and the helping us refine our designs as well. Good data inputs. So what I want to do here is talk about the who, what, where, when, why, how concept, and really demonstrate who this presentation should be focused towards. And it's really focused on land acquisition managers, land development managers, engineers, and designers. These are primary audience for who benefits the most in terms of their workflows from these data sets, from these original grade data sets that we'll derive using LiDAR. And why it's important is it really allows us to understand in the land acquisition stage the risks associated with acquiring that land, knowing what we're getting ourselves into when we're buying that land and about to proceed on a project. We need to quantify that in some way to be able to proceed with some design. And then also in the design stage, it allows us to create grading profiles using this original grade data, or grading plans effectively, that optimize the amount of earthwork on site, that reduce the net amount of material being imported, exported, which has other benefits in terms of working with governance too, and showing that you're actively working towards minimizing the environmental impact. And I'll get into a little bit more of that later for earthwork, as it were, minimizing net environmental impact for earthwork. And then what this is really, LiDAR data is really just the information we're using to derive an original grade profile of a site, specifically targeting the earthen surfaces and extracting that to be able to use that in comparison with our design and know what kind of effort is going to be required to perform work. So we're deriving this original grade data set using a LiDAR point cloud. That's what it is. And then when this is being performed, this is primarily being performed in the land acquisition or in the planning stages for design, an iterative process for design before earthwork's being done. So it can be done in that beginning stage when earthwork has started and general clearing has started, but we advise leveraging this this data set, acquiring this data before the site has been touched, before any work has been done, so that you really understand what you're getting into when you acquire the land. You really understand how to optimize your design before you start doing any work. At least this is our perspective. And then this is an interesting component. So where LiDAR is being performed really has to do with the topographic profiles of the project area and then the amount of vegetation. So historically, deriving original grade data could have been done using traditional surveyor methods. Maybe it's using a total station or a GNSS receiver if you're able to get into the canopy and get good signal, or even just other traditional methods. And you're able to create like this generalized distributed network of data points that you can assume have continuity between them, right? I don't know if you guys are familiar with a tin model, but a triangulated irregular network. Effectively, it's taking all those points and like creating a surface out of all of them. But this has some like bold assumptions about the accuracy of the surfaces, the actual earthen surface between each of those points, which might not be, it's not going to be accurate in cases where there's like high topographic changes, right? As the site changes significantly over some distance, relatively short distance, you're going to see that that 10 model, that representation with low density points is not going to be particularly accurate relative to a LiDAR data set where you're going to have many points per meter or square foot. It'll give you a much better representation of what that earthen surface looks like over space, specifically within these like highly topographic areas. Within fairly flat areas, it's not necessary, but I think it does improve. It will improve the accuracy of the data set you're working with for original grade, because there are so many more points, so many more measurements. But it might not be necessary if you're working with like a fairly flat or a flat site. So yeah, really recommended or highly recommended on areas where there's moderate to significant topographic changes, and then when there's any obscuring vegetative structures or structures in general that prevents being able to measure the site well. Using normal photogrammetry workflows, LiDAR is where that steps in and it really shines and allows you to derive these original grade data sets. There's plenty on where, so how. We already touched base a bit on how in the prior slide regarding like the theoretical component of using laser to measure distances. So I don't think we need to touch much more on that. There's a whole bunch of, that's just the data acquisition component for the LiDAR. There's a whole set of processing components that come thereafter, and then the actual data delivery in our platform is really the end point of that data set for our flows, in which you can export it, but we'll talk about that more at the end. All right, so I want to give a quick introduction to the difference between LiDAR and photogrammetry. And this slide will help illustrate that to a degree. So we have this nice RGB image on the left-hand side here that gets covered up by two other images. And that's just to give you a feel for what this photo is really representing. But you see these taller trees and then these low-lying shrubs and then some exposed earth. So it gives you a feel of like three different levels of coverage, either no coverage with earth, some moderate height shrubs, and then some full-size trees with vegetation like full leaf on. And this middle image that you're seeing that comes in second right here, that's a digital elevation profile, or DEM, that represents the surface of the earth or whatever material as generated by photogrammetry. So it's calculating, you can see all those red bumps in there, it's calculating the elevations of the trees and the shrubs around it. So it's not a great representation of what an earthen surface looks like. And then this last image all the way to the right here is a representative digital elevation model generated from a LiDAR dataset, where you can see the trees have been removed and the vegetation has generally been removed for the most part, and it provides a fairly accurate digital elevation profile for the earth at this particular site. So I want to give a representation of what this central image looks like versus this rightmost image looks like, photogrammetry being in the middle, and then the rightmost being the LiDAR data set for elevation profiles. And you can see how different they are this way. And it really gets to the heart of the technology of what's really being done here, which is represented on the next slide. So yeah, the difference between photogrammetry and LiDAR is really that photogrammetry is calculating the pixel locations the distances between the pixels and the distance from the pixels to the sensor that's taking the image. And that's a way to derive locational data or elevational data, but it's not a direct measurement. It's not like taking the laser and literally taking a direct measurement of that point. So LiDAR allows those direct measurements to occur. So it's empirical instead of derived this way. So it has this benefit of being able to penetrate through foliage, whereas photogrammetry, you see this blue point cloud draped over the canopy and on the surface here of the Earth. That's the photogrammetry derived points that we're seeing here, whereas the yellow is this, or yellow or orange is this point cloud generated from LiDAR data set, where we're able to see these lasers actually penetrating through the canopy, providing a full profile of what the tree looks like and the earth and surface below, and the shrubs in between too, right? So it gives a good full vertical profile of what this profile, this is literally like a profile through a forested area with a road running through it. It gives a good vertical profile of what everything looks like that's in that environment. And this is where we're able to use filtration after the fact to filter out all these tree points and vegetative points above the surface and derive that earthen model below it. So really the biggest difference is that photogrammetry is not able to see through trees and obscuring objects very well. It's averaging all that light in each pixel and blurring out what the ground looks like below it. Even though there is light coming from the ground, it can't see individual photons of light coming from the ground. It averages that out per pixel, whereas the LiDAR is doing direct measurements and it's able to see significantly more accurately what that earthen surface looks like, because it does a significantly less averaging compared to photogrammetry. All right, yeah, and another component here would be cost. That photogrammetry is much more common. The equipment required to perform work and the workflows associated with it are moderately lighter, less expensive, less skill required to capture photogrammetry data relative to LiDAR data. There's just more complexities in terms of how you're capturing that information. It's become easier in the most recent past with new systems coming out, but still it requires a significantly more depth of knowledge to capture the imagery, capture the data, process it, and then deliver it as well. So be the final note on those primary differences. Let's keep going. So I wanted to show here what this really looks like. So this is a colorized point cloud on the top here of a forested profile. This is a 6-foot wide swath of forested environment, effectively, and it's colorized, so it means each of the laser measurements also takes an RGB color point at that location, so it's able to measure the actual color there. So it gives you can see this green canopy coming at the top and kind of a brownish gray understory with there's some shrubs in there as well, and then kind of a light brownish earth below it. So that's the colorized point cloud. And then what we're able to do, like I mentioned in the prior slide, is we're able to classify that. We're able to post-process the data and say, okay, well, of all these points, which of these actually represent the earthen surfaces, which is what we care about, and which of them do not, which of them are a tree canopy or some other obscuring object. And then we're able to classify them and filter them out and literally strip off all of the points that aren't relevant for the earthen profile. And you'll see that it looks a little fuzzy here, and that's because it is a 6-foot wide swath. It is a swath. It's not just like a nice clean, like 0.2 foot width. It's much deeper than that. So it's going to be a bit fuzzier because it's also accounting for changes in elevation and the depth of the image too, right? Because there is a representation in depth here. All right, so that's the primary components of LiDAR in terms of its theory, its strengths, and how it's generally able to create these earthen profiles, so we're able to filter out the data and generate this specific original grade data set. Let's think about how that information, these original grades, independently of how they're derived, whether it's LiDAR or otherwise, how that can be leveraged to perform our normal workflows. So thinking about like suitability analysis for these projects, we're really thinking about it, removing all this tree canopy, being able to look at what the topographic profile looks like, and determine whether or not that land is going to meet the specifications that we have within our own project's definition, whether that's risk associated with performing, developing that project, or the costs associated with performing some level of earthwork, or risk associated with governments related, like floodplain analytics, and ensuring that we have some known hard threshold, whether we're meeting those known hard thresholds for risk associated with development in certain areas or sublocations of that project. And then what it also it helps us detect existing features too. So if you're acquiring land and you really want to know what you're getting yourself into in terms of the additional features that might be on that project that were not permitted or were deposited there by people, this data set helps illuminate those as well. So you might see a number of cars that have been left or parked in this abandoned land, or this land that those vehicles have been abandoned, and you might be able to quantify how much disposal you have to accommodate for, and this will illuminate that in an earlier stage in the project rather than doing it at the clearing stage and finding those things later on. Or maybe might be unpermitted structures that you're also able to detect and highlight too. So there's some other added benefits to LiDAR that can help illuminate these issues earlier on and reduce the risk of proceeding on a project by having full transparency into what you're acquiring at that land acquisition stage. So there's the suitability component. Continuing on. Yeah, then the real meat of it, which is the designing and planning component. So these original grade data sets allow us, like I said before, stripping off all the vegetation, whatever vegetation type that is. There are a few limits to that. So there are a couple known vegetative types that have problems with being able to derive good original grade profiles in them. There's a particular type of grass in the south that makes it very difficult to see through, and we're not able to leverage LiDAR data sets as accurately as if you were doing an in situ like measurement with poles. And this is known. LiDAR is not able to see through things that no light can penetrate through. So if it's dark on the ground and completely void of light, then yeah, we're not going to be able to measure the earth and surface below that. So we're measuring that most visible top layer of the surface that we can measure. And there's also like higher density grasses as well, in like higher tropical areas, like in Hawaii. There's a couple large, like very tall grasses that again have the same issue where it's so high density and so thick that you just can't see through some areas that have that level of density. All right, yeah, optimizing design for minimal import and export. So another significant component of this would be reducing the amount of materials that are being moved in or out of the site, and really trying to shift the design and the grading plans to really reduce the amount of net import and export. And the objective really being multi-part, right? Not only is there environmental damages associated with import-export that governments are going to care about and that can slow down your project potentially, but there's also just the tangible component of moving so much soil and the costs associated with additional import-export that you might not have been able to plan for or accommodate for without having an accurate original grade. And you're having to bring in more than you expected, or maybe export more than you expected. So this can really illuminate at the very beginning stage what your design should be, or giving you that ability to shift your design to minimize this import-export and minimize the potential risk associated with governments slowing down a project due to concerns for environmental impact associated with that too. Yeah, so these are the bigger benefits to using these data sets that we've discovered in the design stage. Keep going. So I wanted to give a quick view into what this data would look like in our platform. And I chose a profile, this cross-sectional view, to help illuminate what this data set will look like in a very clean way. Because what you see below it, you'll see this red. This is really a depiction, a graphical depiction or visual depiction of a difference between an original grade and a design grade. And that image will be spread across the entire design grade component, and will ensure that we capture an original grade with a buffer around it so that you get your entire design grade filled out with data of the original grade data and being able to compare those very directly. So this is the more useful component than the cross-section tool, because you're able to truly quantify the discrepancies in the design versus the original grade data, and quantify what your net import-export could be like in a numerical sense, right? And not only just in a visual sense, but in a numerical sense. And you can see how you potentially need to move soils across the site. And we can even use our software to plan what your grading would be like within that workflow as well. But this cross-section really wanted to lets you see how you can compare the original grade in a simple profile view to what the design would look like, and have a better feel in a section basis those discrepancies and how you would use that to educate yourself about where soil will potentially be moved in a very simple profile fashion. So, all right. Yeah, so I'll wrap this up here and then we'll jump into questions. I think we have about 9 minutes left here. So yeah, what we need to start on our projects, just in a quick summary, we really want to understand what your project area looks like. We want to understand what existing control might be available, and we want to understand what coordinate system information is associated with that, so we connect directly to your engineer or your surveyor and work directly with them to share that information. And then we want to coordinate on aerial markers as they're required for the work we perform to ensure quality and ensure that we're properly able to compare between our design information that you're providing and the data that we're capturing. If we don't have these GCPs or these aerial markers, then we're not able to directly relate the two, and the value is significantly less, if not massively diminished. So yeah, and then also we need time to set this up. Like anything, it just takes time. But once we have this information, we're able to move fairly quickly. So that's the final components, just talking about what we need logistically to proceed on our projects. So from here, I'm going to move into questions. Let's see here. Yep, thanks for being here. Appreciate it. All right, let me read through a couple and bring that up. 1 second. Yeah. So how much time and cost savings can be achieved by incorporating LiDAR technology in pre-construction phase? Yeah, so so traditional methods of surveying took significantly longer to acquire this information, right? You're moving a person through the high density forest potentially, and taking lots of laser measurements with potentially a total station, and it just takes a lot of time, a lot of man hours to go through that process and acquire a final product that's able to be very usable as an original grade. So this LiDAR data sets, they're significantly faster in being able to acquire that information. And they're significantly less expensive as well, because the amount of man hours and time it takes to process that data is much lower than traditional surveyor methods. So yeah, it's significantly faster and lower cost from our perspective. How well does LiDAR pick up on existing grass on sites? Yeah, so good question, Chris. So LiDAR does a pretty good job of picking up on existing vegetation. It will detect whatever's on site and be able to take direct measurements of it. And the type of grass, that, like any object, the larger the object, the easier it is going to be able to detect it, but the harder it's going to be able to penetrate through it if it's a continuous surface. So it really depends on the type of grass to know how well it'll be able to detect it, or any feature that is independent of whether it's vegetation or some structure. So you could take rebar, for example, right? I mean, anything that has a really thin diameter or thin surface area, it's going to be significantly harder to detect that with LiDAR. But for the functionality of what we're trying to derive, right? We're trying to derive this original grade surface. The amount of density of points that we need isn't overly saturated. We're not trying to detect individual points within a centimeter area. We're trying to detect individual points in this meter kind of area, right? So it allows us to take many points across the entire project, remove all the thin features, the thin grasses and obscuring objects, and be able to really detect what we're going after. So yeah, it really depends on the size of the object you're talking about. But existing grass on site, for sure, we can see that, and we're able to filter much of that out as long as we're able to see the earthen surface below it. It's not so thick that we're not able to see through to the bottom. How does groundwater affect LiDAR data? Okay, so yeah, water does impact. This is from Brad. Water does impact the ability for LiDAR to detect the earthen surface below it. So certain lasers have been designed to detect earthen surfaces through water, but for the majority of work that we perform, we do not use we do not use that type of technology, because it's just not frequent that we need to detect bathymetric data. There are cases where that is true, and yes, we would go to that technology at that point. But for the 99%, we're not leveraging that type of laser. So we're leveraging a laser where it does not travel well through light, or through, it travels well through air, but not through water, excuse me. So when it hits a water surface, it will deflect off and not give accurate measurements from the bathymetric surface, or the bottom of the pond. So this is generally where we're going to have to make assumptions around what the profile is, or elevation profile is, whenever there's water on site. And this is where weather does impact when we're able to capture data, and the current pond or water conditions, ponding conditions or water conditions on the project. So we'll have to delay acquiring data until either those have been drained, or make an assumption that in those areas where there is any ponding, that the surface model is just going to be the surface of the pond. We can calculate what that surface looks like and then flatten it out, effectively saying this is what we think the earthen surface is going to be like. But really it's not an accurate assumption, in the sense that there might be some deeper contouring, or we don't know what kind of depth of contouring is happening in that water area. So yeah, best to have our LiDAR data acquisition occurring when there's the least amount of water on site to get the most accurate profile. But if the ponding size is pretty small, then the amount of deviation from reality really isn't that significant from our perspective. Can we deliver in DWG format, excuse me, and or the point cloud format? For sure, yeah. So we're able, this is from Mark. Yes, Mark, we're able to derive data sets in pretty much whatever format you want to be able to, well, for one, we're definitely providing in our software to make it easy for you to use and compare within our tools, but for sure we're able to generate LIS files, DWG files, TIN files, pretty much whatever export you're really looking for to bring into whatever software you want. You can work with us in that process, and we're able to derive the right exports for you to use across whatever team you're trying to satisfy, for sure. Not a problem. Can LiDAR detect the difference between water and dirt? This is from Chris. Yeah. So LiDAR can detect differences between water and dirt in a couple ways, right? I mean, but really it's not so much like LiDAR itself, because LiDAR doesn't think. It's more so like the technician, the individual who's processing the data. Yes, they're able to detect, generally speaking, where there is water and where there's dirt, and then make assumptions around how to process that data and filter the data properly to generate an accurate elevation profile of the earthen surface there, or as accurate as we can be, right? Again, if there needs to be a very accurate profile of the earthen surface in some large ponding areas, then it would make sense to wait for those ponding areas to be fully drained to derive the elevation model you're looking for. So LiDAR in itself, the data in itself, the innate sensor will not tell you it's water or dirt, but the person who's interpreting that data, and that's why we have a human in that process, in that chain of processing the data, to determine and classify which points should be thought of as actual earthen surface versus not. I hope that answers the question you're looking for, Chris. All right. I'm just reading through a couple here. Does a LiDAR workflow differ significantly when compared to photogrammetry workflow? Will I need GCPs to perform LiDAR surveying? This is from Chris. Yes, for sure. We require ground control on all of our projects that we're performing. We're sticklers for accuracy and quality, so we're unwilling to proceed on projects without having some level of quality control installed. And we perform all of our flights using RTK or PPK workflows, so the innate accuracy of the data will be fairly high in itself, but we still want the ability to perform like independent QC checking in this manual process, where we'll georeference those markers in, and we'll be able to give a quality report. So part of our deliverables is showing the quality of the data we're delivering relative to known benchmark points, these flight marker points. And so did I answer the question all the way there? Does it differ significantly between photogrammetry? I'd say it's about the same for photogrammetry. There can be a little bit less from our perspective, but they're pretty much comparable. If you're using RTK or PPK, the density of the network can be pretty much the same for RTK and PPK. When you're using non-corrected imagery, then yes, there's a significant volume more of GCPs that would be required for that. Okay, and we're pretty much out of time here. I'll see if I can have another quick one, and then we'll wrap it and call it. Depth that yeah, is there a depth that it can handle? Let's say a foot to deal with rain events. Right. So yeah, LiDAR. So the question here is, to what depth within water can LiDAR detect earth and surfaces or materials in the water? And the most absolute answer is that it depends on the laser. It depends on the hardware that you're using. Because the physics of it essentially states that a laser is hitting water. And when it hits water, the light's going to refract. And when the light refracts, its measurements as it comes back to the receiving entity or the receiving sensor on the LiDAR unit is going to be diffracted, and it's going to essentially not represent a perfectly accurate representation as if it were just traveling through air, because it assumes that it's moving through just air instead of through air and water when it's taking measurements. So the absolute answer is that if a laser is moving through, or this LiDAR unit, this LiDAR data photons are moving through the air and it hits water and it diffracts, it's not going to provide as accurate of as a solution as if it's only moving through air. And therefore, with those water measurements, you will get some hits along the edges where the water depth is not very deep. But the accuracy of that information is going to be questionable. You'll get a bit of depth into it, but it's really not it's not trustworthy. So we like to make the assumption that whenever there's this ponding, or whenever there's water, we're choosing to flatten that out. We're choosing to say, here's the water's top surface. We're not going to represent any of the bathymetry, any of the base of that pond or water body, because we're not confident in that data that we're providing. So, all right. Yeah, I think that's all we're going to go for the moment in terms of time. I appreciate you being here, and thank you for all the great questions. I'll make sure that we get back to you on all these, and yeah, hope you all have a great day, and feel free to reach out to us if you have any more questions or if you'd like to schedule a demo. We're here for you whenever you want. Appreciate it.